overcome the avalanche breakdown at an earlier stage, we are to overcome the avalanche breakdown at the earlier stage. So we are going to change the shape of the diode internally. Externally, the diode looks same. It might look like this, or it might look like this. The diode can look like this. Okay, where it will be having a silver lining here, so that indicates cathode. This is how it looks practically. But actually, whatever you are seeing, no, that is the covering. There will be a plastic covering. Inside that, the material will be there. So what they are going to do is, to overcome the avalanche breakdown at the earlier stage. So to extend it, because we know that once avalanche breakdown has occurred, the diode becomes useless, because we are talking about a normal PN diode. In normal PN diode, avalanche breakdown occurs, and in this case, whenever an avalanche breakdown occurs, during that case, if it occurs a little bit late, then we can use the diode for still more time. So to extend the lifetime of that particular diode, so what they are going to do is, they are going to, all these days we were telling PN, this is P, this is N, two layers are sandwiched together, all those things we were telling. Now what they are going to do is, they are going to uh, change the shape little bit. They are going to change the shape. So what they are going to do is, instead of a rectangular, they are going to make in this shape. So now this becomes the P layer, and this becomes the N layer. Okay, so when they are going to change the shape like this, they are going to make the sharp edges on the either sides. Whenever they are going to make sharp edges to this PN diode, during that time, what happens actually is, at the sharp edges, the electric field will be experienced. The electric field experienced at the sharp edges will be lesser compared to the electric field experienced on the other side. So, because of this, what happens? They whenever avalanche breakdown occurs, you know that the depletion layer is destroyed. So, when the depletion layer is destroyed, during that time, the N layer, the connection will be, see, this is the connection how we are going to do P layer, N layer. So when you are going to, when the current is passing like this, during that time, what happens, when the depletion layer is destroyed, there will be a chances of even losing the layer itself, this layer or this layer, the layer itself will be lost. So to overcome this problem, we are losing the depletion layer. At the same time, sometimes because of higher voltage, over voltage, we might lose the layer itself. So to overcome that, to retain the layer for some more time, so what we are going to do is, we are going to change the shape like this. Sharp edges we are going to make. So whenever you are going to make it sharp edges like this, during that time, the layers, whatever this part of this portion and this portion, these layers will not go off early. They stay for a longer time, because the electric field experienced at this particular portion is different compared to the electric field which is experienced at this particular portion. When the electric field at this particular portion is lesser, during that time, it will not affect this particular portion of the layer. So what is our overall idea is, at least we have to retain some part of the layer for a longer time. We may lose, because we know that there will be uh, modulation effect. There will be a modulation effect. So what is this modulation effect is? So whenever the depletion layer is getting destroyed, along with the depletion layer, even the some portion of the N layer will be destroyed and some portion of the P layer will also be destroyed. So we cannot retain the complete N layer, but we can retain some portion of N layer, some portion of P layer by making this sharp edges. So this kind of making the size of the diode and making it to retain is known as beveled edge. We call it as beveled edge. So this is the beveled edges. Okay, this kind of protection of the diode, this kind of methodology which is used to protection of the diode is known as beveled edge. Along with this, there is one more method called as guard ring. The one more method is guard ring to provide prevent the edge during the breakdown. So what we are going to do here is, this is the side view how actually it looks like. So we are going to make the 3 layers instead of 2 layers. We are going to make 3 layer. We are going to consider 3 layers of the diode. So we are telling 2 layers will be there. Here there are 3 layers, but you will understand, even though it is 3 layers, it is diode only. So what we are going to do is, we are going to can see here half ring. This in this layer, what they are going to do is, one layer will be N, other layer will be P only. Okay. So here, what they are going to do in this case is, uh, the N layer and P layer, the doping will be done, but to the layer of P and one more P layer which is attached, and along with that, an half ring structure will be done. And half ring structure will be done. So whenever an half ring structure will be done, during that time, what happens is, so one first I'll tell why P plus is used here along with P. I want everyone to note down whatever I tell and whatever I write. So I'll be asking the questions again in the middle. So whenever this ring structures are ring structures are done and P plus is done to P. So this P plus will be acting like a ohmic ohmic contacts. Ohmic contact. Any idea about ohmic contact? No idea. So ohmic contact means it is acting like a metallic contact. If, the diode here, I showed the picture of the diode. This is a plastic covering and this is a metallic thread. This is a metallic thread. So here we'll have a metallic thread connection like this. So this will be acting like the ohmic contact. Okay, or the metallic contact, we call it as a ohmic contact. So here the P plus will be acting like ohmic contact. What it is going to do is, it will be acting like a ohmic contact, as well as it is going to protect the P layer, because in avalanche breakdown, as I told, the modulation effect occurs. Because of that, we will be losing the layers, some part of the layer itself. So to overcome or to avoid the early losing of this layer, we will add similar kind of layer along with that. This is normally doped or lightly doped. This will be heavily doped. When it is heavily doped, during that time, the chance of losing the layer will be less. So now, even though this is people, it look like one more layer, but since both the layers are same, this both the layers will be combined and makes it as one single layer. It will be acting like a one layer only, even though it is lightly doped, heavily doped. So this P plus is going to protect this layer, as well as it is going to act like a ohmic contact. To this, you can just insert a metallic thread that will be done. No need of inserting one more metallic thread inside this and so it will be acting like a ohmic contact, as well as it will be protecting this P layer. And coming to this ring like structure. So what is this ring like structure? So what is this ring like structure they are going to do? So these are known as the guard rings. So guard rings, what they are going to do is they are going to isolate the junction where the avalanche breakdown occurs. Because of this kind of shape what we're having, ring like structure, instead of having a flat structure, if you are having a ring like structure, during that time what happens, it is going to overcome the avalanche breakdown for a shorter duration. So such that at least some portion of the depletion layer will be retained for some amount of time. To isolate the depletion layer from the avalanche breakdown, we are going to do a ring like structure, because ring like structure is going to create difference in the electric field. So wherever we are having a flat surface, there the electric field will be same. But during that time, the effect which is done to the depletion layer will be slightly lesser. So that is the idea here. So how we are going to, this is how the guard ring. So how we are going to look how it looks in a rectangular shaped PN junction is, so they'll be doing like this is P layer. Okay, between this N layer and P layer, this is where we'll be having the junction. This is where we'll be having the junction. In this junction only, we'll be having this ring like structure. Because of this ring like structure, what happens, there will be a difference in the electric field. The electric field at this ring like structure will be different. The electric field at the flattened surface will be different. Because of this, what happens, the depletion layer will not get destroyed at the early stage. It will be retained for a longer stage. These are beveled edge and guard ring. These are the two methods which are used in the reduction of the depletion layer. Also for the production of the diode. After this, the next one is the this is the beveled edge what we are having, sharp edges. You can see the ring like structures. So you have a ring like structure. This is going to, and W is the width of the depletion layer. So you can see there is ring like structure, and again some flat surface is there, again ring like structures is there. So you can see here there is a ring like structure and we are having a flat surface. So these are the methods which we are going to use. And because of this, you can see P plus. You can see this is the Fermi level. This is the uh, energy band gap, whatever we are looking in. So P plus N, N plus. See, not only P plus, we can even have N plus. We can add an N plus layer to N, or we can add P layer to P plus layer to P. So, or you can add both P plus and N plus layer together. So we can use in any pattern. So this is unbiased condition. This is reverse biased condition where negative is connected to the positive and positive is connected to the negative. And you can see that since the depletion layer is large, we are having a long slope with the width. Depletion layer, we are having a long slope. Next, after that, we are having the photodiodes. Okay. So what do you mean by a photodiode? You have already studied. What is a photodiode? What is a photodiode? Anybody? What is a photodiode?
Hello, so can you hear me now?
Yes, tell me.
So light into electric
Sir, it
current.
converts light into light energy. Semiconductor,
So it's a device which is going to convert light energy into
light to
electric
current.
Current.
energy. Right? Hmm.
Electrical
So that
energy.
is known as photodiode.
Hello.
Now,
So could you hear me now?
yes, tell me.
Hello.
Yes,
Could
yes,
you
tell me,
hear me now,
Nivedita.
sir?
Yeah, yeah,
Okay.
yeah. I can hear.
Hello.
Yeah, I can hear. Tell me. So photodiodes. So photodiodes are the diodes which are going to converts the light energy into electrical energy. So from now onwards, we are going to study about the photodiodes with photodiodes, solar cells, all these components we are going to study. So in this part, we call it as a second part only, second part of this module. So here we are going to study about the photodiodes, solar cells, photo detectors, light emitting diodes, that is LED, and its materials. So in the photodiodes, what is the basic first step in photodiodes? We know that even this is also a PN layer. This is also a PN layer. So what is the basic phenomenon involved in this? So the basic phenomenon is light will fall on this, and that is getting converted to electrical energy that we tell that electrical energy means current. But where we will be making the light to fall, whether on a P layer, whether on an N layer, whether on a depletion layer, or on the entire surface of this PN diode. Any idea?
Depletion layer, sir.
Where will be making? Hmm?
Depletion layer.
Depletion layer. So here, what we are going to do is we are going to make the light to fall on the depletion layer. Before going on to this study of how actually we are making it to fall on depletion layer, what actually happens inside it, first we'll learn what actually, why actually in why actually we have to make it to fall on the depletion layer only. So in what kind of biasing we do for PN diode? Forward bias or reverse bias in photodiode?
Reverse bias.
Yes. The main thing you should remember is it will be always reverse biased. Okay. Now my other doubt what I have is Why we have to do reverse bias and we have to do all this circus? We would have done it forward biased and easily done it, no? We would have forward biased it and made the light to fall on this. Why we want to make it reverse bias? Then we are making the light to fall on this. Hmm? If I'm going to make it forward bias, obviously current will be more. But why I'm going to concentrate on the reverse bias condition only?
So then the
Hmm.
potential difference across the depletion layer will increase.
Okay, increases. So what happens? Current will increase.
So the depletion layer in forward bias is less, no, sir. But in reverse bias, it's more.
Okay. You are very near to the answer. Okay. So what happens actually is here I want to convert, as the definition itself tells, we will be converting light energy to electrical energy. I want to convert that light to current. I don't want, already some current is there. I don't want to add this converted current to the light. Converted current to the already existing current. I want to convert the light to current. I don't want the light to be converted to the current and added to the light. Say what happens in forward bias? Already the current will be flowing. The current will be flowing in the forward bias. If you make the light to fall, first of all, to make the light to fall, depletion layer will be very, very thin. So you'll be not having much space for the light to fall. Okay. So even though you are going to make to fall the light to fall over the entire PN layer, what happens there? The light energy, which is going to give some amount of or the current which is obtained by converting light to electrical source, will be getting added up to this current which is already flowing. But what I want the light equivalent current. How much light is coming? What is that equivalent current I want? Because basic application is in what happens, we'll be having a photo. Going to do is there is some device, my landline or anything I have. So this is going to give the signal in electrical energy. This is my voice breaking?
Yes, sir.
Yes, sir.
Okay, please tell me whenever my voice is breaking. Please tell me. Is it now okay? Or still, it's the same.
It's better now, sir.
Okay, just a minute. Is it clear now?
Yes, sir.
Or is it same? Hello?
Now
It's
it's
clear
better,
now,
sir.
sir.
Okay. So I was telling the example of OFC. So I have some device, my computer or my landline or anything. So that is going to give out some electrical signal to my communication system where we are having LED. So this electrical signal is getting converted to light, and by total internal reflection (TIR), the light signal is going to travel in the optical fiber, and after that it is going to reach the photodiode. The photodiode, what it is going to do is it is going to convert the received light to electrical energy, that is the current. By using that electrical energy, my other receiver or my friend who is going to talk with me, he is going to get that signal. Here, I hope you can understand now. Here, what this photodiode is going to do, it is going to convert the light equivalent current, or it is going to give the light equivalent current. If you are going to use a forward bias, what happens during that time? Some already pre-existing current will be there. To that, this current will be, or this light equivalent current will be added up. So during that time, what happens? My message will be changed. My message will be changed. So whatever the signal I am transmitting, that equivalent current or that equivalent energy I'll be not getting. I'll be getting some another current. So which is not containing any message, or it might be having any other message. So from this, what we understand is we need to just convert whatever the light received to electrical energy. Okay, so that's why we are going to use photodiodes in reverse bias condition. Whenever we use it in reverse bias condition, during that time, what happens is you can observe here the depletion layer will be more. And see, the W is the width. So width of the depletion layer will be increasing during that time, and there is a condition HV greater than EG. EG is the potential or the energy across this particular junction, and this is the radiation. Okay, whenever this radiation whenever this radiation is greater than this the potential across the depletion layer, during that time what happens is the minority charge carriers which are already stuck in this particular junction, they start getting activated. Because of that, they start flowing. So to whatever direction, see, electrons has to flow towards this direction. They will get energized and they start flowing, because they, in the n layer, what are the minority charge carriers, and p layer, what are the minority charge carriers we have? In n layer we have holes as minority charge carriers. In p layer we have electrons as minority charge carriers. But since the depletion layer is very large, this minority charge carriers which are present here, they cannot come here, or the minority charge carriers which are here, they cannot come here. So making the light to fall on this becomes a waste task. So that will not give you any current. So that's why what we are going to do is we are going to activate, or electron hole pairing is done to the charges which are present inside this depletion layer. So when the light falls on this, these electrons which are already stuck here, so they get energized. Because of that, they start moving. So this movement creates small amount of current. So more the amount of light which is falling, more will be the current. So you can observe here in this particular graph, this is the forward bias condition, this is the reverse bias condition. So here you can observe GOP is equal to 0. GOP is equal to 0 means when the G means generation rate. When optical generation rate means the generation of the charges because of light, so is equal to 0, because this is the reverse bias condition, reverse bias graph. But that's why GOP is equal to 0. But when light starts falling on this depletion layer, during that time, what happens? The current starts increasing. You can see that G3 is greater than G2 is greater than G1. So whenever the light starts increasing during that time, even the current might be reverse biased in the opposite direction, but there will be increase. So to whatever voltage you are going to, you might increase whatever the voltage from the battery, but the current will be keep on increasing. This is the one level, G1 level, G2, G3. So let us assume some fixed amount of light is falling on this. So during that time, G1, I'm going the light is further increased and it is made constant. Then this is the amount of current we'll be obtaining. And again, the further the light is increased, and then this is the amount of current we are obtaining. So from this, we understand based upon the light which is going to fall, the current is going to increase. More the light, more will be the current. So now from this, what we are going to do is optical generation is going to take place. Optical generation in a PN junction. This is the junction, PN junction. The optical generation, even though light may fall on every place, but still the concentration will be more on this depletion layer. Okay. So why can't this start flowing? Because they cannot overcome the depletion layer. So that's why what we do is we energize the charges which are already stuck, which are already placed in this particular junction, and because of that, they start flowing. So GOP indicates the optical generation, IOP indicates the current because of optical generation, the current due to the optical generation. So current due to optical generation is given as QAGOP into LP plus LN plus W. Q is the charge, A means it's the area, to how much amount of area it is going to fall. So usually it is measured in per centimeter cube. So how much more the area of the depletion layer is being absorbing the light, more will be the current, optical generation will be more. So IOP, the current, optically generated current is directly proportional to the charge across a particular area. If the light falls for a more area, more current will be produced. GOP means generation rate because of optical generation. So optical generation means because of the light, the electrons, a whole pair are going to generate. No? That is GOP. So what is the rate of this? So again, IOP is directly proportional to the generation rate. More the generation rate, more will be the current. After that, LP. LP indicates the length of the P layer. LN indicates length of N layer. This length of P layer, length of N layer, and W indicates width of the depletion layer. So based on all these things, the optically generated current is going to depend. After that, I is equal to I is directly proportional to ITH e to the power of QV by KT minus 1 minus IOP. So along we know that thermally generated current will also be there. Thermally generated current will thermally, because of light falling, we will be even having the heat will be generated. Because of that also, some amount of charges will be generated. So thermally, so total current is equal to thermally generated current minus optical current. That is the actual current which will be flowing finally. Okay. So after this, the same thing we can rewrite it as I is equal to Q. This all the formulas you have to remember because we are not going to have any derivation for this. So I is equal to QA LP by tau P into PN LN by tau N into NP. So this tau P indicates we have already discussed about tau. What is tau in the semiconductor device? What is tau? What does tau indicates? What is tau? It is the mean lifetime of the holes. Tau p means mean lifetime of the electron. Tau n means. So Pn, LP indicates the LP indicates the length of the p layer. Pn indicates number of the uh, uh, the n type of charges, that is minority charge carriers in p layer, that is electrons in p layer. Np indicates number of holes in n layer, because in n layer holes is the minority, in p layer electrons are the minority, that is indicated by Pn. Ln is again length of the n layer, tau n is lifetime with respect to the electrons. Np indicates the number of minority charge carriers in n layer. So, and again, this is for the ITH, we are substituting this particular part, and e to the power of qv by kt minus 1, that is our diode equation what we are already having. And IOP, we have already the equation. This equation we are going to substitute here. So that gives you the total current. All these equations are necessary in finding in the problems and all. We need this equations. Okay, so we'll stop it here today. So, and we can continue tomorrow in the next class.